We'll have his regular office hours on Friday, and we still have a regular discussion. That's all I have. Any questions? No? Okay. Yeah.
There was a slight typo in the...
Yeah, it's due Friday, not Saturday. I need to fix that, yeah. Yeah, I haven't gotten to that yet. Yeah, sorry about that. Other questions? Okay. So we are on the topic of building communication systems now. We've done our background, we've done our modeling, and we can now talk about how to design encoders and decoders to maximize data rate and minimize power and minimize error probability and so on. So I'd like to kind of build this up in stages. So we study how to build communication systems for kind of a simplified channel model first, and then kind of add complexity to it. So last week we looked at how to communicate over channels without ISI. In fact, the H matrix was identity. So we studied how to communicate over the channel if your H matrix is identity and you have no synchronization errors to worry about, synchronization trouble to worry about, and you have no uncertainty about what the H matrix is and so on. And we have I think a reasonable understanding of that problem at this point. There's a lot more to say, and we'll loop back to it when we talk about coding, but we have a basic understanding of that. So now I'd like to start ratcheting up the complexity of the channel model step by step. Okay. So next step is to look at channel models that are diagonal, but not necessarily identity or scaled identity, and then we'll go from there to talking about ISI. Okay. So first topic for today is communicating over diagonal channels. Okay, so let's suppose our channel model is the following. Okay, so the decoder will observe Y as before. Y will be H of X, where H is what the encoder picks, plus Z. Z is the usual thing. So Gaussian, zero mean, covariance matrix n times I. So the components of Z are IID Gaussian, zero mean variance n. And we're going to assume for this part that H has the following structure. So it's diagonal. And I'll use little h to denote the diagonal entries. Like that. And we'll assume these entries are ordered too. So the 0, 1, 0th one is the biggest. Down to h n minus 1. Okay. So last time we looked at the case where h was identity, so all the little h's here were 1. Okay, so we studied that problem in some detail. If h is diagonal and the diagonal entries are all equal but not equal to 1, okay, then the problem is equally easy, because you can just write it as like, alpha identity x plus z, and then at the decoder side just divide through by alpha. Okay, and you end up with y equals then identity x plus z over alpha, and the alpha just changes your n parameter. Okay, and we solved it for general n anyway, so it doesn't really matter what your n parameter is. Okay, so if h is diagonal, if h is scaled identity but not identity, then the scaling factor you can just absorb into the noise and not worry about it. Okay, so we've done identity, we've done scaled identity. I'd like to consider now the case where h is diagonal but does not have equal entries on the diagonal. Okay, so the way to think about this physically is you have some bits to send, you create a wave file, that's a vector of samples. Okay, you send it through the channel, and this channel is kind of funky. So it takes each sample of your wave file, multiplies it by a different number, which you know ahead of time. Okay, and then at the receive side, you get the wave file with these scalings, and then with noise added on top of it. Okay, so this is a linear time varying channel that we have here, right? Certainly linear, ignoring the noise, it's certainly linear. Okay, it's time varying, and that the gain experienced by an impulse at time 0 is different from the gain experienced by an impulse at time 1, and so on. Okay, as such, it's not clear why you'd consider a channel model like this. Our channel model is LTI, right? Ignoring the noise. This is time varying. Why would you do this? Okay, it's maybe not clear at this point. So you gotta just humor me. Okay, trust me that this will come up. Okay, so when we go to deal with ISI in our channel, what we're gonna do is reduce our channel to one with no ISI, but for which the gains on these different coefficients are different. Okay, so I want to solve this problem first, have a good understanding of this, and then we'll reduce the ComCloud channel to this one. Okay? Okay, so let's suppose first, we wish to send 1 bit, so a single bit. Okay, 1 bit over n time samples. Okay, I don't mean 1 bit per sample. I mean 1 bit total. Okay, so the whole WAV file encodes just a single bit. So your rate's like, you know, 1 over n times the sampling rate. Okay, so the rate's potentially quite low. Let's let u denote the bit that we're going to send. And here's one possible encoder. I guess we need to fix the power constraint before we can talk about encoding. So let's say, let me just remind you, the power constraint is the same as we had before. So it's the time average power over the whole transmission has to be at most p. Okay, this should arguably be like over, before you start talking about sending a bit, because the power constraint is kind of independent of like what you're transmitting, like how many bits you're transmitting. So really, this should be kind of like up here maybe. Set things out of order. Okay, so if we want to send 1 bit, and that's our power constraint, okay, then one possible encoder, that's very reasonable I think, is to encode the bit into the first sample, the one that gets multiplied by H0, and just not even use the rest of the samples. Okay, so set every sample in your WAV file, except for the first one, set those all to 0. Just lock them at 0. Okay? Use the first sample in the WAV file to send your bit, which means you can actually put all that power in the first sample. Okay, so your transmission is going to be very peaky, right? You're going to have like a big impulse at the first sample, and then you're going to send nothing forever after. You can debate whether this sort of like violates the spirit of the power constraint or not. We'll assume this is legit. Okay, so we'll set x0 to be plus square root of np or minus square root of np, depending on if the bit is 1 or 0. Okay, so I'm concentrating all this power in the first sample, right? And you can check the power constraint. So 1 over n, expectation of the length squared of x. This is what? So we have sum over all the entries of x, expectation of that component squared, right? Okay, and the 0th component here, I mean, the length is just the sum of the things squared, right? Sum of the components squared. Length squared is sum of the components squared. Okay, so x0 here squared is going to be np. All the other terms are 0, so we just get p. Okay, so it's using exactly the power that we've allocated to the whole transmission, but it's concentrating all that power just in that first time slot, right? All right. Tell me about the decoder. Tell me about the map decoder. What would it look like in this case? Think first in terms of just the I/O behavior of the map decoder. Like, what is a valid input to the map decoder? What is a valid output? Like, before you even get to the functionality of that, suppose you're going to write a subroutine decoder. Okay, before you even go to code that up, okay, you got to describe like, you know, what is the type of the input and what is the type of the output. Yeah.
I would imagine like you would just look at the first element of y. And see if that's positive or
Okay, so you're jumping right to the functionality of the decoder. So the type of the input would be the whole WAV file, like the vector y, right? The output would be a bit, I guess, for what u is. Okay, so what you're suggesting is ignore, if I understand correctly, you're saying ignore y1 up to yn minus 1, right? And what was the rest of the suggestion? Was there one?
If it's x, if y0 is positive, then u is 1.
Yeah, I'll write it like this. Like that. Yeah. So that is indeed the map decoder. And let me justify this and point out one subtlety that it's easy to miss. So if you write out this equation kind of component by component all the way through, so you have y0, y1, y2 up to yn minus 1. Okay, so the H matrix looks like this, right? Okay, it's getting multiplied by x. And then plus z. Okay, so the z components are all independent, right? These are IAD Gaussian, okay? All the signals get encoded right here, right? And all these are locked at 0, right? Our encoder is such that x1, x2, et cetera, are all locked at 0, okay? So if you're the decoder, you get n samples, right? You get a wave file consisting of n samples, okay? All the signals in here, these ones are just noise, right? No signal in x1 through xn minus 1, because these are all 0 here. So you're just picking up the noise. Okay, so indeed it is optimal to just ignore these and just decode based on y0, which reduces just a scalar problem, which we've solved already. There's one subtlety here you got to be careful though. We're using crucially the fact these z's are independent. Okay, remember we had a homework problem on this? We had a setup very similar to this where you had noise that was dependent across the components. Okay, and in that case, if these noises are dependent, even if there's no signal in a particular component, it can still be useful to use this as part of your decoding, the corresponding output, because it tells you information about this noise, which tells you information about this noise, which tells you information about that signal, because you're observing y0. Okay? That does not happen here though because the noises are independent. Okay? So the equivalent thing here is like, you can imagine the channel kind of sending you y1, or y0, excuse me, and then it just generates a bunch of like independent samples that are just pure noise and just hands them to you. Like it's pretty obvious that's going to be these are going to be useless to you. But it's because the noise here is independent of this. The noise here is independent of this noise. If these were dependent, that would not be the case anymore. You need to use the whole vector. Okay, but they are independent. So we can drop all those and just use y0 alone. Okay, so the error probability. So you can write out the error probability in our usual way, do troll probability over u. If you want to do it pictorially. You got to think in terms of the received signal if there's no noise. The received signal if there's no noise is either h0 square root of np or minus h0 square root of np, right? These are like the two possible signals, two possible received signals. You got to be careful. Like the transmit amplitude and the receive amplitude in the absence of noise are not the same here because of the h scaling, right? Okay, so the two possible received signals if there's no noise are these two. So the error probability is going to be the chance that the noise pushes you this distance, right? So that's going to be square root of, I'll write it as h squared 0, np divided by n. Right? Okay, compare this to the following. If we send one bit over the kth sample instead, rather than the 0 sample. Okay, suppose we use the kth sample in the wave file and we put all the energy on the kth sample and send the bit using the kth sample. Okay? Can run through all of this. The only thing that's going to happen, you're going to get hk here instead of h0. Like that. Right? Go through the same reasoning. If the bit's encoded in x2, you ignore y0, y1, y3, and so on. You decode just based on y2. You threshold it with 0. Okay, you're just going to have h2 here, h2 here. Picture all go through. You'll just have h squared of 2 rather than 0. Right? So in general, for general k, this is the error probability you get. How does this compare to that one? We have a working assumption here that I've erased that's important to answering this. Yeah?
So HK is less than or equal to H is 0.
Yeah?
So it's less, like argument of Q is smaller, so error probability
Should
is
be
larger.
bigger. Yes, exactly. So we're assuming, if you go back to your notes at the beginning of the lecture, we're assuming the H's are ordered. H0 is the strongest, then H1. Okay. So if you just put it in H0, you're kind of putting all the signal in the sample that gets the biggest gain or the least attenuation in the channel. These other ones attenuate more. Okay, so you can think through it mathematically, like this H is smaller, therefore the argument to Q is smaller, therefore the error probably is bigger. Or you can think of it just in terms of like engineering, the physics of it, like these gains are smaller, the attenuation is larger. Okay, so the performance should be worse compared to this one. Okay, so if you have one bit to send and you're going to put all of the energy in one sample, that first sample, the 0th index sample, is the one to put it in, right? It's the strongest one. Makes sense to put all your eggs in that basket. You can show if you're going to send a single bit, it's not advantageous to put it in another sample or to spread it over multiple samples. Put it all in the sample that gives you the biggest gain. That's for one bit, though. Suppose you want to send k bits instead. This is maybe not great notation here because I'm using k in two different ways here. Let's going to call this m. Not that it really makes it. It's kind of a dummy variable, but call that one m maybe, just so we don't confuse this sample here with the number of bits that we're sending. Okay, so just use m as the dummy variable here. I didn't write that very clearly. Okay. If you send all k bits over the 0th sample, so if you send all the bits over the 0th sample using PAM, using M array PAM, 2 to the k array PAM, okay, the error probability is going to be about 2q. And then remember our error probability for PAM, it's got 3 times the power, which is np, h squared 0, divided by 2 to the 2k minus 1, n. Okay, I put approximate because this assumes that like all the points are internal. We're ignoring the slightly lower error probability at the edges of the constellation. So kind of ignoring edge effects right here by putting 2 there. In general, the probability is going to be slightly lower than 2. Okay, so we can write down the error probability or a close approximation to it if we send k bits over the 0th sample. All right. Now, when we're sending 1 bit, we said you're best off putting that 1 bit in the 0th sample. Okay. If I have k bits to send, is that still going to be the right thing to do? The best strategy? What do you think? Let's just do a really quick vote. Okay, I'm just kind of curious people's intuition here. So this is like totally non-binding. It's non-graded, but everyone has to vote. Okay, so just pick one. I'm not going to call on you and ask you to justify your vote. Okay, but just pick one. All right. So 2 possibilities. If the goal is to send k bits for an arbitrary k over this channel, 2 possibilities. One is it's optimal to put those k bits on the 0th sample. Just do 2 to the k array PAM on H0. Or on x0, leave x1 through x0 idle as before. That's option 1. Option 2 is split the bits out. Put some on H0, some on x0, some on x1, some on x2. and so on. Possibly leaving some unused, but the point is in option 2, you're not putting them all on X0. So how many people vote for everything on X0? Leave the other samples idle. Okay. How many people go for splitting the samples over, splitting the bits over several samples? Not everyone's voting. Okay. All right. Good. Wow. Okay, your intuition is good. Did I lead the question too much? You guys just have really good intuition about communication. So so I promise I wouldn't call on anyone to justify their vote. Would anyone like to volunteer to explain their reasoning? Go ahead. Yeah.
Doesn't it depend on age, I would think? I mean, like age 1 to age n-1 could all be 0, right?
So I guess, so option 1, as I described it, was for any h's that are ordered in the way I describe, and for any k, you're best off putting all the energy in the 0 sample. Okay. Option 2 is there exist scenarios where they're ordered as I described, and there exists a k so that you're actually best off putting some energy in X0 and some in some other sample. Because they are exhaustive that way. Yeah, so everyone voted for the second possibility. Anyone care to explain the reasoning? Yeah?
I guess like if you have like a given power,
Yeah.
when you try to use pen to, you have to like divide the range that you have like so much if you try to put it all in.
Yeah. So that's the way I think about it. So I can elaborate a bit. So I think it's helpful to think about kind of adding an additional bit. Suppose you've got like k bits that you're sending with X0 and you're not using any other sample. Okay. So now you want to send another bit now. You want to go from k to k plus 1, right? So what's the best way of doing this? So you've already got k bits on X0. So the X0 sample is divided into like 2 to the k different signal points. Okay, and you're worried about the noise pushing you from one to the other. As k gets really large, eventually the signal points are really close together. Okay, whereas in the other samples, it's like wide open. There's nothing there. So for a given amount of power, I mean, you can put these signal points far apart, right? Okay, so that's indeed what happens. You start adding bits. Okay, eventually, even though the other samples experience less gain or more attenuation, they're less crowded. Okay, and therefore it's advantageous to put bits on those two and not just on the 0 sample. Okay, but if that's the case, then this potentially gets very messy, right? Like suppose I want to send k bits. I've got a fixed power budget. I want to send k bits. How do I allocate these? There's a huge number of possibilities, right? For where I put the bits and where I put the power. I can allocate the power how I want. I can put some on 0, some on 1, some on 2, right? How do you match the bits with the power? Should samples that have more bits to send, should they get more power? If the H is weaker, should it get more power to overcome that? Or should you kind of put the power where it counts, namely where H is bigger? Like many possibilities, okay? So, ultimately the definitive way to settle this is to do like simulations, okay? But the search space is huge, okay? So what we're going to do a little bit of theory to try to get a rough handle on what the best strategy is for allocating power and bits among samples in this kind of situation. Okay, and that gives you like a starting point, and then in practice you can always like numerically optimize around that analytical solution. Okay, so this is called bit power allocation. And again, you have to kind of take on faith. I'll call it power allocation procedure. Maybe we finish that. You have to kind of take it on faith that like this is a useful procedure. Right now it looks very abstract. Like why would you have a channel like this? This is kind of weird. So you have to kind of just trust me that like channels we'll deal with, like the channel in lab 3, okay, and the channel in lab 5, okay. We're going to reduce both of them to this style channel, okay, and then the difference between lab 3 submissions that work okay and those that work great, okay, is in part whether people do this procedure. Okay, or whether they just kind of blindly just send all the bits on one sample, or send put equal number of bits on all the samples, or whatever. Okay, so let's focus on the n equals 2 case first. Okay, so you just have 2. Should I draw it out? The whole system just has 2 samples in it. In Y, in H, in X, and in Z. Okay, and you can pose the problem multiple different ways depending on what you take as given and what you're trying to optimize. Typically in practice, you have an error probability constraint and a power constraint, and you're trying to maximize the rate. That's usually the way it works. I mean, there are certainly like situations where it works in a different direction, like you're given the data rate and you just got to optimize the power to meet that rate. But usually it happens the other way around. So I'll pose it that way. So let's let's say suppose the overall power P and the error probability tolerance, all right, PB bar for the tolerance as opposed to PE, which is the actual probability, are given. Yeah?
Is there any particular reason why the indexing for 0 Z is 1?
Because, no, it's because I'm not paying attention. Yeah. 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 One thing I learned about, I'll just like quick aside here. One thing I learned about myself a long time ago is I'm not really very good at thinking and talking at the same time. And this, you might argue like I'm in a terrible line of work for someone who can't think and talk at the same time, but I've mostly overcome it, but sometimes when I'm talking, like I'm not really thinking, and so if I could just silently write all this up, it'd be flawless, but you can't do that. Okay. So we can take these two as given. The overall power budget is given, and the overall error probability is given. All right, now the question is, how do you allocate the power among the two samples, 0 and 1, okay? And how many bits can you communicate total with this much power and this allowable error probability? And how do you allocate those bits among the two samples? You put them all in the 0 sample, all in 1, split them. How do you split them, okay? So here's the optimization problem. So we'll say let K0 and K1, I should say Ki, denote the number of bits we send over the ith sample. Okay, and let's let P sub I be the amount of power we're using over the ith sample. Okay. Then the goal is to maximize K0 plus K1, maximize the total number of bits you're sending. Okay, over, we get to pick K0, K1, P0, P1. Those are the decision variables, as they call them in optimization. Those are what we pick. Okay, then we have constraints. So subject to following constraints, P1 plus P2, upper bounded by 2P. This is the n here. Okay, the 1 over n in the power constraint, that 1 over n becomes, NP. And the error probability of the system, the overall error probability of the system is upper bounded by this error probability tolerance, P bar. Okay? So it's like any choice of K0, K1, P0, and P1 that satisfy these constraints, you use no more than the total allotted power. And the error probability of the system when you do, 2 to the K0 array PAM on the 0 sample and 2 to the K1 array PAM on the first sample, the overall error probability for that system should be no more than PE bar. Okay? So this is the optimization problem right here that we want to solve. Given the power budget, given the error probability tolerance, how do you allocate your power? How do you allocate the bits? And how many bits can you send? Okay? So like I said, the definitive way of solving this is really to do it numerically, but we're going to do like an approximate solution analytically, just to get a feel for it. You can always kind of optimize around that numerically. Okay, any questions? Is it clear what problem we're solving? Yeah? Question? No? Okay. All right. So let's solve this. So first of all, we need an expression for the error probability to plug in here. So PE is like a function of K0, K1, P0, P1, right? So I want to plug that function in, and then we'll have something just purely in terms of like these 4 variables. It's not there's no digicom left at that point. It's just like an algebra problem. So let's solve for PE. So this is PE is the probability you have an error in at least 1 of the K0 plus K1 bits, right? That's the error event. Okay, so we're not, go ahead, yeah.
Why is less or equal and greater or equal?
Why, sorry?
The constraint, why is less or equal? I said 2, okay.
It's a 2, yeah. So n is, so this is our power constraint, right? N is 2 here. And this here is P0 plus P1, right? So P0 plus P1 less than or equal to 2P. Yeah? Okay. All right, so we're going to solve this exactly. We're going to do an approximate solution of this. And here's the first approximation right here. So we're called the union bound. Probability of A union B, upper bounded by probability of A plus probability of B. This requires no assumptions on A and B, right? They don't have to be independent. They don't have to be disjoint. It's always true. Look familiar? Where have we seen this? Have we? Where? Homework 1, yes. It actually comes up various places in communication system engineering. So here's one. This is not the most prominent use of it in communications. Okay, so using the union bound, okay, we're going to say the error probably is upper bounded by the chance of an error in the x0 bits plus the probability of error in the x1 bits. And, the bits you send on x0 and the bits you send on x1. Okay, so this event right here is the union of this one and this one. Okay, so we're just going to upper bound it by the probability of the sum, the sum of the probabilities. Okay, and moreover, and the reason for doing that is that we have expressions for these events, right? This is just the PAM error probability, right? I'm sending K0 bits over x0. So Ki bits over Xi with power Pi. Okay, so I can just write down an approximate formula for the error probability for this. 2, ignoring those edge effects. Q of, you have Hi squared NPI, n is 2, divided by 2 to the 2Ki minus 1, n. Like that. Okay, so if we plug this in, the overall problem becomes max the sum of K0 and K1 over K0, K1, P0, P1. Subject to, sum of the power is less than or equal to 2P. And then we're going to have the sum of these two PAM error probabilities less than or equal to P bar. So I've got H squared 0, 2P0, 2 to the 2K minus 1, n. That's in the first Q function. Second Q function, 2Q square root of, I have H squared 1, 2P1 over 2 to the 2K1 minus 1, n. All that less than or equal to PE bar. Okay, so all I'm doing is I'm taking the error probability of the overall system. We're upper bounding that, or approximating it by its union bound. We do that because we know an expression for each of these probabilities individually. Probably the union not so much, but each of the two individually we have an expression for, so you plug that in and you get this optimization problem. Okay? People with me so far? Okay. So I'm going to approximate this further. Okay, so consider the similar problem wherein we just, rather than saying we want the sum of these two to be upper bounded by PE bar, I just say I want each of these terms individually to be no more than PE bar over 2. It's a more stringent constraint. Okay, if each of these individually, if that term is less than PE bar over 2, and this term is less than or equal to PE bar over 2, then the sum is upper bounded by PE bar over 2. Okay, I'm going to replace this constraint with that more stringent one. Okay, so my error probability constraint becomes just that 2q square root of h squared I, 2pi over 2 to the 2ki minus 1 n. That less than or equal to PE bar over 2. And this will be true for I both 0 and 1. Like I said, it's an approximate solution. Okay, we're not doing like an exact analytical solution of that. I'm kind of making some approximations here and there to make this tractable. Okay, so we do a union bound, and then we impose, instead of having like a pooled error probability constraint, which is what we have over there, we just impose an error probability constraint on each of the samples individually. They each get half of the error probability budget, if you want to think of it that way. Yeah? Okay, the reason for doing this is that now I can solve this for ki in terms of pi and then reduce the dimensionality of this thing down to just 2 variables instead of 4. Okay, so take this equation, divide through by 2, and take q inverse of both sides. And q is a decreasing function, right? So you're going to take q inverse of both sides, you flip the inequality. So flip the inequality, and we have h squared I 2pi over 2 to the 2ki minus 1 times n, right? Okay, so let me move the 2 to the 2ki minus 1 over and put everything else on the other side. So this has to be less than or equal to what? H squared I 2pi over n q inverse PE bar over 4, right? Good question. Yeah. So we need to square the q. Thank you. Yeah. So that's squared, and that's squared, right? Yeah. Okay, divide by 2, take q inverse, square. The inequality flips when you take q inverse, and then rearrange. Yeah? Okay. Another approximation. Ready? I'm just going to ignore the 1. Okay, so what you get is ki should be about 1/2 log 1 plus This is the SNR over the ith sample, right? Pi over n. And then times a bunch of stuff. You've got the gain over the ith sample. You've got a 2. You've got Q inverse of PE bar over 4 squared. No 1 plus, I guess. That's if you keep retaining the 1, which I actually want to drop that 1. So just 1/2 log that. Okay? That is a base 2 log, yeah. It cancels this. It's canceling this 2 to the power. Okay, so that's just a rearrangement. Now, so the beauty of writing things this way is that it expresses ki in terms of pi, okay? And the goal in our problem here is to maximize each of the k's. So think about the p's being fixed for a moment. Suppose hypothetically p0 and p1 were fixed, okay? For that fixed p0, p1, you'd ask, well, how large can I make k0, k1? Right, because I want to maximize the sum. Well, k0, k1 don't appear here. They only appear in this constraint. But this constraint is ignoring the -1s, equivalent to this one. Let me just write it as, maybe let's write it like this. Okay, we want to make k0, k1 as big as we can. How high can you go? Well, this is as high as you can go. You go higher than this, and then your error probability constraint is violated here. Okay? So if we're given p0, p1, like this is the largest you can make k0 and k1, are given by this formula here. Okay? So this effectively reduces the problem down to a 2-dimensional optimization problem. Okay, you really only have p0 and p1 to play with. Once you fix p0, p1, k0 and k1 are sort of fixed by that formula there. You just put those there, right? And then you're optimizing over k0, k1, or optimizing over p0, p1. Now, the k's have to be integer valued to do PAM, right? We have no integer constraint here. There's no guarantee this thing will evaluate to an integer. Okay, there's another approximation we'll make. We'll just sort of ignore that. Assume we can send like fractional bits with PAM. Okay, so we're left, yeah.
As like an intuition thing.
Yeah.
Given all the assumptions that we've made so far, does this expression evaluate to a model that it's an overestimate or an underestimate? So, yeah, that's my question.
So we were consistently more conservative than we needed to be up to here, right? So we only overestimated the error probability of the system in doing the union bound. And then when we constrained each sample to have error probability at most PE bar over 2, that's again like overly conservative, right? So we're getting sort of a like pessimistic bound. That's up to here. Now the other approximation is I dropped the 1, right? So that is, so if you write it like this, so I guess it's also pessimistic when I drop the 1, right? That forces me to use a smaller k, right? So overall, this should, I call it an approximation, but it's really like an underestimate of the k. I'm thinking about it that way too. Yes, good question. Other questions? Okay, so if I just substitute in for k, I get an optimization problem purely in terms of the p's. So plug in for k0. Plug in for k1. Trying to maximize that sum over just p0 and p1 now. Those are the only variables left. Subject to the constraint that the sum is at most 2p. Okay? Now let me separate out, in the objective here as we call it, there's a lot of stuff that doesn't really depend on the p's, right? You've got 1/2 log base 2 p0 times p1, right? Let me pull out the p1 and the p0 and combine those, and then you're going to have everything else. 1/2 log, do I need to rewrite all this? Just everything else. Okay, so extract, I can write this as 1/2 log p0 plus 1/2 log all this other stuff, plus 1/2 log p1 plus 1/2 log all this other stuff. Take the p0 term and the p1 term, combine them, lump everything else together. That's our problem, right? So what's the answer? How do you allocate your power? So to solve this, we can ignore the this additive term here. I mean, if you're curious about how do you optimize this, like how do you choose P0 and P1 to maximize this subject to this constraint? Obviously, this additive term doesn't do anything, right? It changes the final value, but it doesn't change how you allocate the power. So you ignore that. Likewise, the half doesn't do anything. The log doesn't do anything, right? Really, what we're asking here is how do you maximize the product of two non-negative, I should say, quantities, subject to a constraint on the sum. So what's the answer? Sorry? It should be equal, yeah. Oops, I wasn't supposed to erase this. Say it again.
The giant reduction.
Oh, how do you go from here to here? Yeah, okay. So you have this, right? So I'm going to use this fact a bunch of times, okay? So the P0 is my A, and all the rest of this is B. So you get 1/2 log P0 plus 1/2 log all the other stuff, plus 1/2 log P1 plus 1/2 log all this other stuff. Okay, and now the other stuff here, recombine them into one huge thing. The P0 and the P1, combine them into 1/2 log P0, P1. Yeah. Other questions? Okay, so uniform power allocation is actually optimal. So if you have two numbers, and they sum to 2p, okay, then the product less than equal to p squared. Okay, that's an upper bound always, and you'll hit that upper bound if and only if the two powers are the same. P0 and P1 are the same. Believable, right? No? Not believable? Each one could be 0. H1 could be 0. Yeah, so so I guess I just erase this here, but like, so what do I have here? P, if I can do this from memory, P1, H1, 2 divided by n q inverse PE over 4 bar squared. Like that. Is that what I had there? Yeah? You have it written down. I don't. Yeah, so you get 2 of these. Like that, right? So the square is evaluating that, right? Yeah, so I kind of pulled a bit of a fast one when I kind of formally applied this. So actually, this thing is, if h1 is 0, I'm going to get log of 0 here. That's minus infinity, right? So that can't be right. That says I send minus infinity bits. I can always just send 0 bits, right? That's always a possibility, right?
It could also be like 0.00.
Good. So this is an excellent point. So the trouble, no, you're absolutely right. So yeah, I mean, this with h is 0 here, this is going to cause us various problems here. In particular, this can't be the number of bits we send because the value is to minus infinity, right? The number of bits I can send is always at least 0, okay? So there's some trouble here. The trouble comes from dropping the +1 over here, okay? So in the really low bits, low power regime, that +1 is kind of important. And if you save that +1, then you won't have this problem, but then the power allocation ends up being not quite so clean, okay? You gotta use Lagrange multipliers and stuff to do it. So I kind of skate over that. So I guess we're kind of assuming that the h's are large enough, that the k's are large enough that the 2 to the 2k minus 1 is about 2 to the 2k, and you can ignore the 1. So there's that kind of like high SNR assumption kind of baked into this. Yeah. Does that answer your question? Hopefully, yeah. Okay, so it's an approximate solution, and there's certain approximations, you know, intrinsic to this. Okay, so if we assume we're in that regime, we can drop the +1, then the h's have got to be, you know, reasonably large. So that's not going to happen. So then we are just left with this problem. Okay, so I claim the solution to this problem is to put the same amount of power in the 2 samples. Is this believable to people? Yeah? How would you show it? Would you not bother to show it? You just say it's reasonably clear. Don't waste time proving things. That's, I think, a very legitimate view. I mean, I've stated in a very mathematical way. Maybe it's easy to get distracted by all this language here. But if I just want to show that, like, the best allocation here was to put equal power between P0 and P1. Like, forget about all that. Just think about this optimization problem right here. How would you show the best allocation is to put equal power here? Any thoughts? Yeah?
Graphically?
Yeah, graphically, yeah. So it's really like a one variable problem, right? Because like clearly you want to use all the power, right? You shouldn't choose P0 and P1 that give you a strict inequality there, right? You shouldn't leave power on the table. But then like P1 is just 2P, which is like a fixed number given to you, minus P0, right? So you only have one free parameter really. And so you just plot this as a function of that one free parameter and you'll see it's maximized in the middle. That's one approach. I'll show you a math proof that I think is really slick. It's like, this is sort of proof where it's like, it's not clear how you would think to write this, but you know, it's if you follow line by line, it's like immediately convincing. So consider the difference of the square roots of the 2 powers squared. So I mean by not so intuitive why you'd prove it this way, but just consider this quantity. That's certainly not negative, right? Expand the square. That's P0 minus 2 square root P0 P1 plus P1, right? So move the square root to the other side, and you get 2 square root P0 P1 upper bounded by P0 plus P1. P0 plus P1 is upper bounded by 2P. So square root P0 P1 has to be upper bounded by just P, I guess. Right, end to end, cancel the 2's. Okay, and you'll get equality if and only if you have equality right there and right there. Those are the two inequalities that led to this one. Okay, so you'll get equality here if and only if you have equality right here and right here. So that happens if and only if P1 plus P2 equals 2P, and they're equal. So they've got to both be P. Okay, or you can plot it. Okay, or you can do calculus too. Once you have a one-dimensional problem, you can take derivatives and so on. I guess this maybe amounts to doing exactly this. Okay, so what the math says to do, modulo these approximations we're doing, set the two powers to be the same, and the number of bits you send in the ith sample, choose to be 1/2 log base 2. Here we go again. Oh, here it is. 2 pi h squared I over n q inverse pe bar over 4. That quantity is squared. That's it. Okay, so modulo these approximations, if you have a power budget and you have an error probability budget, and your goal is to send as many bits as you can, and you decide how many bits to put on each sample and how to allocate your power. Okay, the math says put the same amount of power on both samples. How many bits you send in each sample is not the same, however. It depends on the strength of the channel, the strength of the sample. Okay, so a sample that H0 is stronger than H1, so H0 will tend to get more bits than X1 does. Because of that right there. Okay. Now this is an approximation. Okay, it tends to be valid in the kind of large K regime for reasons we just discussed. In particular, it can happen that you can easily get h's such that you set the powers equal. You go to compute this, you get something negative here. You get something less than 1. Okay, so in that case, what you do is you just choose that k to be 0. Just ignore that sample. Don't send anything over it. And then resolve the problem with a smaller set of samples. Okay, so take the samples that aren't getting any power, aren't allocated any bits, allocate them 0 power. Okay, and then just essentially just ignore those samples and then resolve this thing for a smaller set of samples that have higher gain, and keep doing that until eventually the math tells you to put bits on all the samples you have left. Okay? That's for 2 in general. So for general n, set P0 equal to P1 equal Pn minus 1, and Ki choose to be 1/2 log. You're going to have n Pi h squared I over n q inverse of Pe bar over 2n. So there's like 2 2's here. Okay, one of them was because n was 2, the other one was not. And that's squared. Hang on a second. Why do I have a 2 here? When I put this up, I asked if this is correct. People said yes. But is it really supposed to be a 2 here? Sorry?
Wasn't that little m? You said little m is 2.
Yeah, but this is ultimately what goes there is the power. So when I started, I was putting all of the power in one component. So I had expressions like this, like that. But now I'm not putting all the power in one component. I'm putting P1 as the power in this component, not 2P1. I think this should probably just be P1 here. Here. When I did the big expansion we talked about, was there a 2 in there? Yes? Oh my gosh. Why do we get a 2? Where did that 2 come from? Really? I wish we could rewind the video recorder and I could see, I mean the 2 must have come from somewhere, right?
Can you put in where it said the probability error and there's one that's, you put it in that expression.
When I did what?
You do the probability of the error in the x1 bit.
Oh, okay, if I have k,
You said 1 bit over the M.
okay, yes, then all of the power is being sent over the mth sample, and all of the power is NP. So yeah, if you send all of the power over the mth sample, then like the power over the mth sample ends up being N times P. Right? If I put, this is like all the power I've got, right? Like this is my constraint. Like that. Right? So move the N over, you get like that, right? So this is the sum of the squares, you know, sum of the expectations of the squares of each of the components. So if one component carries everything, it gets Pn, right? But, so in that case, like Pm is equal to Np. So if you want to write, instead of Pm, you can put Np, or you can put Pm, but you don't want to put Npm, that'd be that, right? So I don't think there should be a 2 here or here, and therefore not here or, and no N here. I didn't catch it until I went to write N there. Sorry. So bottom line, here's the solution. Okay, so the math says set all the powers to be equal across the samples. And then how many bits you put on a particular sample is a function of that power, which is the same across all the samples, and also the strength. The strength of that sample. Okay, and like I said, it can happen, you go to solve this, you get a negative value for ki. Okay, that's because of the approximations that we did, particularly dropping that -1. So in that case, just drop that sample from the system completely. Just ignore it. It's too weak to use. So just drop that sample. Consider a smaller dimensional system where that sample doesn't exist. Just rerun this calculation. Allocate all the power uniformly among all the other samples. Go to compute the bits. And just keep doing that until eventually you have a system where you're allocating power uniformly over a subset of samples, and they're all getting bits according to this bit allocation. Make sense? Yeah, I mean, ultimately, this this boo-boo here about the 2 is like, in some sense, it's not that big of a deal because, like I said, in practice, you would numerically optimize this anyway. Okay, so in practice, I can tell you what you do. You start with the mindset you're going to allocate the power uniformly over all the samples, okay, and use this as like a rough starting point to figure out how many bits to put over each sample. Ultimately, then you simulate it, okay, or test it, see what error probability you get. If it's smaller than you're targeting, okay, then you can try to add a bit here or there. If it's, you know, if it's too big, you pull back on bits. But ultimately, like the acid test is really like a numerical simulation or just an experiment. Okay, so just kind of get you started. I think this intuition here about the power being equal is interesting. It's not what I would have guessed a priori if I didn't know, if I didn't do the math. Because you can argue lots of different strategies, right? You can argue like putting more power on the weaker samples, right, to sort of overcome their weakness, give them more power to, you know, power through the noise, right? Or you can say, well, you should put the power where it counts, and you get more bang for your buck with the stronger samples because their gain is bigger. So put more power on the stronger samples. Right? And you can, like, qualitatively, you can argue many different ways, right? Somehow these effects kind of cancel each other, and the math does do a uniform power allocation. Okay. Okay, one small aside, like suppose you go through that whole allocation and you get like math tells you k equals 2, k0 equals 2, k1 equals 1. So you send 2 bits over the 0 sample, 1 bit over the 1 sample, right? So your constellation then looks like this, right? Eight points, 2 to the 3, right? So if you're the receiver, you're going to get, a wave file consisting of 2 samples, let's say, and it's one of these 8 points plus noise. Okay? Tell me about the map decoder. So I'm the receiver. I observe 1 of 8 uniformly distributed points plus additive Gaussian noise. So what does the map decoder look like? Hello? You know what I'm asking? Is it clear what I'm asking? Is it too simple to ask? Is that the issue?
Divide the space equally.
Divide the space equally. I'd argue you don't really divide the space equally. In fact, among the 8 points, you mark to the closest, right? So when you have a set of discrete points that are uniformly distributed, you're trying to detect which one in the presence of Gaussian noise, then the map reduces to minimum distance, right? So it's the minimum distance rule is the map rule here. So given a received wave file, which is 2 samples, you just map it to the closest signal point, okay? So the decision regions, as we call them, would look like that, right? Maybe I should draw in a different color, but you get the idea, right? So you have 8 regions. They're not all equal size. I mean, they're all like infinite volume on some level, but these edge ones are somehow bigger than the middle ones, so they're not quite all the same. Okay, I draw this up here just to make one point that's like almost obvious when you draw it up like this, but I think it's worth stating. If this is your constellation and you need to decode it, you don't need to take your wave file, which is a point here, and compute its distance to all 8 separately of these signals here. You don't have to compute this distance and then this distance, this one, like that, okay, and then compare and take the minimum. Because you see the structure of these decision regions, you can just compare like this, the y1 component. Is that above 0 or below? Okay, and then take the y0 component and just compare, is that below this threshold, in this range, or in that range, right? You see what I'm saying? Like you can just decode, like you have 2 bits being sent in this direction, 1 bit being sent in this direction. You can decode them completely independently of each other, right? You can decode this bit just by looking at this component and thresholding it on 0. You can decode these 2 bits by just taking this sample and just comparing it to these 3 thresholds, okay? And that'll be faster, okay, than computing all 8 of these distances and taking the minimum, okay? With 8, it doesn't make a huge amount of difference which way you do it, okay? But, we're going to start looking at problems where n is really big, okay? In that case, if you try to enumerate all the signals and compute the distance, it takes forever, okay? It's like slow enough, never even run. It doesn't even complete in a reasonable amount of time, okay? So I think when you draw it up like this, it's kind of obvious, I think, but I do say it because, if I don't draw it up, it's maybe you don't necessarily think of it. And I've had students come to office hours and their labs, just the decoder never finishes running, okay, because they're trying to compute all these distances to all the signal points, and there's too many of them. Okay. All right. So any questions on the diagonal case? We good? Yeah.
So back to what we have in the Q function for our error probability.
Yep.
Wasn't there a 3 in there somewhere from MRE? Where did that go?
So for Emery Pam, It was 3 p over 2 to the 2k minus 1 n. Was that it? Yeah, when we first did PAM, we didn't have an h, right? So, but then if you have an h gain in here, then you would get like that, right? Yeah. Good, yeah. So yeah, that 3 should be in there. Yeah. You're right. Yeah. So yeah, we should have had 3. Maybe that's why I had a... Yeah. Yeah, not too good. So one advantage of posting typed lecture notes is that you can kind of sort all this through, I can sort all this through, on my own in the comfort and privacy of my home office without, everyone watching me, and then I catch this stuff. So I haven't posted the lecture notes for this part yet, right? So I'll do that. That has this calculation worked out just like I did on board, and I'm very careful about the constants and stuff. Okay, so the main takeaway I can't emphasize enough is like just the conclusion here that you've kind of put equal power on all the samples, and the number of bits that you put in each sample is then not the same. It's a function of the strength of the sample. Okay, so that qualitative conclusion is independent of the 2's and the 3's and the n's and so on. All right, so we have 3 minutes. Maybe I'll quit while I'm behind and not try to do more damage here. So no lecture Thursday, no lecture Tuesday because of fall break, right? And then, so a week from this coming Thursday, we will talk about how to extend all of this to the case where the channel has ISI. All right, so we'll figure that out, and then we can talk about, there are multiple ways of doing that. I'll show you kind of a way that's conceptually simple, but kind of hard to implement first. And then we'll talk about a way that's easier to implement, but conceptually a lot more complicated, which is the way we'll actually use in the labs. And then we'll talk about what to do when you don't know H and synchronization, and then we'll be good to go. Yes, sir.
Given that the exam is coming up, I think it's October 19th.
Uh-huh.
What lecture or what topic is the cutoff for material?
Good question. So I will blast out like what I call it the prelim announcement that has all that information. It has like where the exam is and what the coverage is and the rules and so on. Maybe since we have 2 minutes, we can just do one logistical thing right now. So the format of the prelim, I am open to many options. We can do like completely open everything, open note and open homework and everything. We can do closed everything, okay? You can do the crib sheet thing where you bring one 8.5 by 11 sheet of paper and that's it. Naturally, I write the prelim a little bit differently depending on the rules, so keep that in mind. So I'm game for anything. I usually put this to the vote of the class and let you all decide. So maybe since we have a minute, we can do that right now. So 3 options: closed everything, one 8.5 by 11 crib sheet, open everything. Who prefers closed everything? 2, closed everything. 3, 4.
Can you talk about how different these are?
I mean, yeah. I mean, if a completely closed book exam, you can't. I have to kind of write it in a way. I mean, I don't want like. You don't remember the definition of some particular thing, and then you can't do this entire problem. Like, so when I write a closed book exam, I got to be really careful about that. So I'm careful to write it to make sure I kind of include the definitions in it and stuff as much as possible, so that just forgetting one thing. I don't want it to be just like a pure memorization exam. Whereas if it's open everything, then it can kind of be more like the way the homework problems are in the sense that they don't define. They don't necessarily redefine stuff that we talked about in class. So that's that's probably the main difference in my mind. So yes.
Did you do last semester?
We normally do the crib sheet. I mean, this is my 5th time teaching this class, I think. People normally vote for crib sheet, but sometimes I'm surprised. Sometimes we get surprises. Yes. All right, so let's start again. So closed, everything closed. 1, 2, 3, 4, scaring people off. Crib. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, okay, whatever, about 13. I'm just curious, open everything, anyone? 1? Okay, so we'll do this. This is typically what people vote for, and it's what most of the practice prelims were written in that format. Okay, so sorry about the 3s and the 2s and so on. My mistake. I'll post notes that will have that written very clearly. And have a good fall break.